Now, in this video, we're going to continue on what we were talking about before with the calculation that was done with a weak acid buffer. And it was, I'm just going to show the two sides. The first video, we did the weak acid buffer, and we were adding these two pieces, these two impurities, two different situations. And we were doing this with a full buffer, a proper buffer. So we had a liter with that it was 0.1 molar with the acetate ion and 0.1 molar with acetic acid. What we're going to do now is answer the question about, well, what happens if you only have one of them? So, for example, we're going to say, well, what if you did the same experiment, but it wasn't, you forgot to put some of the buffer together, so you only have the acetic acid? We're going to show that, well, the general idea is we're going to show that it doesn't really work. You know, you'd think it could possibly do something, but it doesn't really work. It's still different from just using pure water, but it doesn't really work the way a buffer is supposed to work, which is to greatly resist changes in pH. So let's see how this is going to go. So we're going to have 0.1 molar HAC. We're going to have 1 liter of it. Once again, still think about the volume and the molarity. So that's 0.1 moles of acetic acid. And that's it. Nothing else. So now we're going to add in our impurity. Once again, I look to see the moles in the volume, etc., so that I can make sure the molarity in the volume if needed, but I make sure what the number of moles are of my impurity. So let's say, for example, we'll take the first one. It's going to be 0.01 moles of HCl. So we're going to put in 0.01 moles of this strong acid. And again, in reality, your impurity shouldn't be this high, but you know, we're really beating up on it to show what happens. So this, let's start by saying, what's the base pH? We did this one and the last one, and we could use the Henderson-Hasselbalch equation because we had a buffer. This is not a buffer. Remember, the way you do this is with your Rice table, and you use your C0, which is 0.1 molar, and your Ka, and you will get your pH. You can't use Henderson-Hasselbalch because the only way you've produced any acetate is by this acting as an acid. So you'll have this tiny, tiny amount. You can't use Henderson-Hasselbalch in that kind of situation. So what we would do to get this is we'd have H plus, and again, I'm doing this very quickly because we've done this sort of thing already. It's the square root of C0 times Ka. And what you end up doing is getting a pH of 2.87. So first of all, it's more acidic than if you have the salt in there, but remember, that's consistent with the common ion effect. If you put in the sodium acetate, it won't be as acidic. We actually had something along the lines of about 4.74 last time because we had 0.1 moles of acetate, so pH was pKa. So this is going to be our comparison, right? Last time we were comparing the 4.744. This time we're going to compare to 2.87 just to see how things change. So let's look at what we've got. If we've got HAC, okay, all we have in this solution is the equation that's in this Rice table. So we have HAC equilibrium, right, because it's a weak acid, H plus acetate. I'm being lazy and not using the H3O plus. Now the HCl is going to be dissociating 100%. Okay, so as soon as this stuff's gone into solution, you've basically got 0.01 moles of H plus and 0.01 moles of chloride. That's it. It's gone into solution. It's dissociated. So let's look at our Rice table here. So what we're going to say is that as this impurity goes in, this is a little bit of an odd way of thinking about it because you're actually going to kind of pretend like the acetic acid is the thing being added and the HCl was already there. And the reason it works this way is because what's going to happen is as this dissociates 100%, we're going to get lots of H plus because of that, you know, relatively speaking, right? All of this is going to become H plus and Cl minus. What this is going to do is it's going to disrupt Ka. And that's what we're going to show over here. So we had our Ka happily doing its little equilibrium thing, and over here, you know, we figured out what the pH would be. Now what we're going to do is mess it up, and the common ion we're bringing in is actually H plus because of this strong acid. This is illustrating something else. A strong acid will suppress the action of a weak acid. So let's show what happens. initially, before the impurity came in, what we had was 0.1 moles, right? 0.1 moles of acetic acid, okay? And if we were trying to figure out the pH, we'd say this is approximately 0, and then this would have been approximately 0, okay? And then we would have had 0.1 minus x plus x plus x. That's what we would have had over here, just the 0.1 molar acetic acid solution. But now we've dumped this in, so we have to take that into account. So this is no longer going to be the background 10 to the minus 7 from water. This is now actually 0.01, which is a lot bigger than 10 to the minus 7. So now my I, but if you look over here, we still have a 0. So even though you'd think, well, adding all that H plus is going to suppress this, we can still see how much it's going to be suppressed by going ahead with the calculation. This is a 0, so it still means Q is 0. We're still going to have minus x plus x plus x. We're still going to do that. But again, it's common ion. We're going to see the effect of this suppressing it. So we've got 0.1 minus x, we've got 0.01 plus x, and then x here. So if we go into our Ka expression, 1.8 times 10 to the minus 5, and you say, why am I not using Henderson-Hasselbalch? We can't use Henderson-Hasselbalch. But isn't there a value here for acetate? What we're going to find is it's very tiny. Remember, we put all this extra H plus in, it's pushing it backwards. This is going to be a very small number, and trust me, you're not going to be able to use Henderson-Hasselbalch for this. We would have had to have had reasonable amounts of both of these to start with. This is not a starting amount that's reasonable, it's 0. We're going to make a tiny amount, so no, you can't use Henderson-Hasselbalch. So here we go. What we're going to have is our two pieces here, right? H plus and AC minus. So that's 0.01 plus x times by x over 0.1 minus x, all right? So we can do our approximation, knock that out, and we get our x, okay? And what we're going to end up with is a value of x, which is 1.8 times 10 to the minus 4. And if you actually go back and look, this is actually, it's roughly 2% of your original 0.01 moles, all right? So basically, you're only going to add another 1.8 times 10 to the minus 4 moles to this. So a very, very tiny amount. So we can't go with that. All right, so this is what we got here, all right? And then we can see from this that x is really, really tiny. So basically, H plus is still pretty much 0.01 molar. In other words, pH from impurity. The impurity itself has completely dominated the pH. So the pH is going to basically be the negative log of the H plus concentration. And if we look at our H plus concentration, this was all going on in a liter, okay? So I'm going to just stop here and make a quick point. This was all done in molarity and moles because I used 1 liter. If I was using a concentration, which is what I should be doing here, I'd have to take all of these and divide by a volume. So technically every one of these is divided by a V, you know, down here as well. But because it's 1 liter, I got away with it. If not, I'd have to divide all of these by 1 liter to get the final values. All right, so what I can see is my H plus concentration is basically, i.e., negative log of basically 0.01. If you want to add 1.8 times 10 to the minus 4 to it, you know, it's going to come out like over here. So it's going to make a tiny, tiny difference. And that's why the pH comes out to be pretty much 2. Right? Pretty close to 2. It's something like 1.98 if you were to even include that 1.8 times 10 to the minus 4 just to see what gets put in there. So let's go back up here and see what that means. Okay. Now, if you compare in the previous video when we put in 0.01 moles of strong acid into our buffer solution that had 0.1 moles of acetic acid and 0.1 moles of acetate, the pH change was less than 0.1 units. Now, if you look here, you've got a change in pH of around about 0.9 or so units. Okay, so much bigger change. So what this is meaning is it's showing how this doesn't really work properly as a buffer. It is a pretty terrible buffer, basically. It's not doing its action. Before we had a factor of 10 difference, and so that shows why you need both parts. Now let's look at what would happen if we put in the basic impurity. Okay, this gets a little bit more involved, but the same idea. We have to think about what reaction we're going to have. So this is 0.01 moles of sodium hydroxide. So we're going to have 0.01 moles of NaOH. Let's do my R, my I, my C, my E, see if we can fit it in. Oops, there we go. And we're going to have our acetic acid. And now we're actually going to make some salt. So here we go. We're going to make sodium acetate and H2O. To start with, we have none. That doesn't matter. And over here, we had 0.1 moles. So again, I'm doing it in moles, and then I can convert to molarity at the end if I need to do, if I wanted to do it using the Ka expression, which I could do. But I'll show you why we can shortcut it a little bit. All right, so same idea as before. We have limiting reagent. This is going completely. Why is it going completely? This is not a conjugate acid-base pair. This is not something that's a weak acid or base equilibrating with water. This is an base, a base, and an acid, and they're going to react together. So we get minus 0.01, minus 0.01, plus 0.01, plus 0.01. Not that we really care about that so much. All right, so what we end up with is nothing here, 0.09 here, 0.01 here. Now, if you look, what do we now have? We have a buffer. So we've created a buffer as a result of putting the impurity into the thing that wasn't really a buffer. So the irony is now it's turned into a buffer, funnily enough. But we already put the impurity in, so you kind of miss the point there, right? If you do that. So let's see, we can use Henderson-Hasselbalch to do that. So we can say, right, pH equals pKa plus log base over acid. So let's go ahead and put those values in, shall we? All right, pKa. Well, this is acetic acid, so the negative log, since it's 1.8 times 10 to the minus 5, pKa equals 4.744. And then we have over here, base over acid. My base is my acetate ion, not worrying about the sodium ion, so this is 0.01. And this is going to be 0.09. All right, so look what we're going to end up with. This is going to come out to be minus 0.954. So what we end up with is basically 3.78. So this drops by basically a whole pH unit. And so let's compare with what happened when we were having the acidic impurity into this sort of half-made buffer. When we put the acidic impurity in, what did it do? Because we only had the acid, it suppressed the action of the weak acid. So what we ended up with is figuring out that our concentration of our H plus was pretty much all due to this strong acid's enormous contribution of H plus, relatively speaking, because it's disrupting, it's dissociating 100%. So we ended up with the pH going down by almost a whole pH unit. And then this time, when we put in the basic impurity, yes, we actually created a buffer as we did it, because we actually finally created a significant amount of acetate ions. But even if we had gone and taken these and made them into concentrations by dividing by the volume and going into the Ka expression, okay, up here, we'd have had to written out this equation again, but we would have had different numbers here. What we would have ended up with is still 3.78. So the pH went up. But the point is, notice it's increasing by around about 1 pH unit. So that's a factor of 10 change in the H plus concentration, whereas before it was 0.1. So you can see it makes quite a significant change in the difference. Now I can't say it's because it's a change of pH of 0.1 units, it doesn't quite work because it's logarithmic, but you can definitely see that if you're changing by 1 pH unit, you have a pretty significant change of H plus concentration. If you're changing by a less than 0.1 of a pH unit, you've got a much less of a change of H plus concentration. So again, what this shows is if you don't have both parts, it doesn't really work properly because the ratios get more significantly disturbed, and so it's just not going to work as a buffer. A proper buffer needs both parts. I would not consider this a buffer really because I didn't make the buffer until I put the impurity in, so that wasn't a buffer to start with. So that's why I'm saying you need both parts for the buffer. So a little bit of a strange calculation, but it does show that the buffering action as a result of putting the impurities in is not really there compared to when you have a proper buffer with both parts of the conjugate acid and base.